Bismillah. My presentation entitled Sol-Gel Silver Doped Zinc Oxide in Films for Optoelectric Applications, Synthesis and Characterization. Work plan. First, we start with introduction. Secondly, experimental part. Thirdly, results and discussions. And fourth, we close with conclusion. Introduction. Context. One of semiconductor material that can be used in optoelectronic devices is zinc oxide. Particularly, doping in zinc oxide thin films with appropriate elements like silver offer an effective way to adjust their electrical and optical characteristics. Zinc oxide material. ZNO has attracted extensive attention during the last decades, owing to its outstanding chemical, electrical, and optical properties, such as semiconductor with wide direct band gap, high transparency in the visible and near infrared spectral region, large exciting bending energy, and other properties not described. All these properties have made ZNO a material of choice for many applications. For example, it used as photocatalysts in photovoltaic cells, as anti-reflective layers, optical waveguides, optoelectronics. Several techniques were proposed for the fabrication of ZNO thin films. Among them, sol-gel deposit method has many advantages. Sol-gel process. Sol-gel process is a wet chemical technique and involves several steps in the following chronological order: hydrolysis and polycondensation, gelation, aging, drying, densification, and crystallization. The main techniques used in the sol-gel process are spin coating and dip coating. Objective: elaboration by the sol-gel dip coating method thin films of silver doped zinc oxide for their use in optoelectronic applications. In this work, silver doped zinc oxide thin films with various moderate doping concentration 3, 6 and 9% were prepared on glass substrate by sol-gel deposition technique. Microstructural, morphological, optical properties of pure and doped zinc oxide films were systematically investigated. The optical wave properties were also considered using the UV visible spectrum. Experimental part. Synthesis protocol. In this work, the molecular precursor is zinc acetate dehydrate, which is dissolved in ethanol and monoethylamine for doped films. Silver nitride was added to the mixture with an atomic percentage fixed at 3, 6 and 9% of silver respectively. This solution is converted to gel by respecting the following steps. Experimental part. Characterization technique. The effect of moderate silver doping, less than 10%, on the microstructural, morphological, and optical properties of such films are investigated by X-ray diffraction, scanning electron microscopy (SEM), atomic force microscopy (EFM), and UV visible spectrophotometry. Interesting results were obtained. Structural results and discussion. Structural properties. X-ray diffraction shows that all the films possess a polycrystalline word-side structure with the axis 002 preferential orientation and exhibit a minimum residual stress. Morphological properties. CMEP graphs and AFM images show a dense surface with more or less spherical grains uniformly distributed. Moreover, it's found that increasing silver doping levels leads to a decrease in grain size and surface roughness. Optical properties. The UV visible measurements have shown that the non-doped zinc oxide sample is highly transparent with an average transmittance of 83% in the visible region, with increasing silver concentration from 3 to 9%, a decrease in average transmittance from 80.2 to 78%, and the blue shift in the direct optical band gap from 2.238 to 3.255 electrovolt have been observed. Conclusion: non-doped and silver-doped zinc oxide tin films have successfully been prepared on glass substrates by the sol-gel deep coating technique. X-ray diffraction spectra have shown that all films exhibit the hexagonal word-side structure with high C-axis orientation of the crystallites perpendicular to the substrate surface. Moreover, increasing silver doping concentration have been found to decrease the crystallinity and inhibit crystallite growth. SEM and EFM images have revealed that the non-doped zinc oxide film demonstrated homogeneous and smooth surface consisting of small grain-sized particles, whereas increasing the silver doping concentration resulted in films with smaller grain size and smoother surfaces. According to UV visible measurements, the non-doped zinc oxide in films is highly transparent in the visible region, with an average transmittance of about 83%. As the concentration of the doped silver increases, the transmission slightly decreases. Moreover, the direct optical band gap is found to increase with increasing silver doping concentration. The high quality of C-axis oriented silver doped zinc oxide in films with minimal stress and tunable optical properties suggests that these films may have good applications in optoelectrics. Thank you for your attention.